Hello everyone, now we're going to learn 13.3, which is arc length and curvature. So in this section, it includes two parts. So now we are going to do the first part, arc length. Firstly, let's have a quick review what we did in chapter 12. So for the parametric equations, f equals ft, y equals, okay, let's use x equals xt here, and then y equals yt, and z equals zt. Used to remember what's the arc length formula, so which is given by this one, right? Which is dx dt square plus dy dt square dz dt and square and then dt. So this is what we learned in 12.2, I think. And the t is the parameter, and then we have the parametric equation here. And then now in general, so actually our curve is given by like RT, so it's just similar to that one, very similar. So RT, which is given by XTI, YTJ, JTK. This is our smooth curve in space, right? So the definition, let's take a look. The length of a smooth curve and the curve is given by this RT, and here T from A to B. Okay, that means, because this means the path T, like for example the particle move, so when T goes, how long is that curve? The length of a curve, okay, yes, this one. The length equals integral from A to B dx dt square plus dy dt square plus dz dt square and then dt. Okay, but now we are going to write this in another way. So if we take a look at, let's see, that means what? If we have a vector, think about the vector. The vector equals v1, v2, v3. What's the length of this vector? The length equals root of v1 squared plus v2 squared plus v3 squared, right? Okay, so now let's take a look at what is in our integral. Actually, that's the length of our derivative vector. So it's like if we have r equals xt, yt, zt. Okay, and what is r prime? Oh, what is dr dt? Same thing, they're the same thing, just different notation. So let's use the same notation here. So which is dx dt, is that right? And the dy dt, dz dt. And what's the, if we take the length, dr dt, the length is just a root of dx dt square plus dy dt square plus dz dt square. So sometimes, for the length, we can also write down this way. This is just the length of r prime t and dt. Okay, two ways. The second way is like the vector way. So those are the two formulas for the arc length. Two formulas. Now let's take a look at the example. Okay, so let's see. We have a helix. Okay, so we have a glider. It's shooting upward. along the helix, and which is given by this vector function cosine t I, sin t j, and here t k, because t goes up an x y satisfied circle. So how long is the glider's path? From 0 to 2 pi. Okay, so if I draw the graph of this one, you can take a look. That is, so helix, right now we draw is move along here, right? So it's like 0 to 2 pi, something. The next is going up. So something like this. What's the length here? Okay. So we're going to find the length from 0 to 2 pi. And now we can just use the formula directly. So let's take a look. L equals here a to b, which is 0 to 2 pi, and the square root, okay, dx dt, which is negative sine t, dy dt, cosine t squared, and dz dt, so z is t, so dz dt is just the root of t, which is 1. Is that right? And we do dt. And simplify. Here sine squared plus cosine squared, which is 1. Okay, I can write down one more step. But whenever you see sine squared and the cosine squared, you know we can always combine them. This is integral 2 pi. This equals 1, so which is root 2 dt. And this constant, we can just take the constant out. So the final answer is root 2 times 2 pi, and which is 2 root 2 pi. This is the final answer. Okay, we can try a very similar problem. RT is given by this one, 2 cosine ti, 2 sine tj, root 5 tk, and here t from 0 to pi. So whenever we talk about the arc length, the boundaries for t will always be given. And here, let's take a look. And you know, you can also do another way. I can show you the other way. We are going to use the second formula. Is kind of like we calculate r prime t, which is you can calculate from here negative 2 sine t, cosine tj, root of 5k, and then we calculate r prime t length, which is root of, you know, it's 4 sine squared, 4 cosine squared, 5, so which is 4 plus 5, and it's root of 9, it is 3. So actually the L equals 0 to pi, length of this one, dt, which is 0 to pi, 3 dt. So the final answer is 3 pi. Okay, so here I showed you the other way to do the arc length, but you know, actually they're the same thing. You can choose whichever you like. So this is the arc length problem. Next definition is called arc length function. Definition 2. So arc length function. Let's take a look. What's the meaning of this arc length? So if we have a curve and the t from A to B, for example, if the curve is from this point to that point, and right now the arc length function means our t going to be a variable, like a t is not from A to B. So for this case, for example, from A to B, that's definition 1, right? So right now our t is from A to a variable, like a maybe changed, okay, to another like a variable x. So it will give us a function. So definition is given by this way. So let's take a look. ST, this means arc length. ST means T naught to T, and here, let's take a look. Because we already used the T as like the function, the variable T, so in the integral, we need to use another variable. You can use any one. Here we use like a tau, okay, d tau. And here is also the same thing, dx x prime tau square y prime tau square z prime tau square. So it's same as like if we say t naught to x, and here you still do dx dt square and the dy dt square, dt square, dz dt square. But you know, because we want to make them consistent, so that's why we like to choose this to be t, and we change this variable into just another any variable. You can also use u, doesn't matter too much. Okay, here we just use the tau. Now let's take a look at the formula. Okay, this is the formula, and okay, the formula we can also write down this as t naught to t. Here, same thing, right? R prime tau theta. Okay, and let's take a look at the example. I will show you why this is a function. Why it's called arc length function. Example 2. Here, RT is given by cosine Ti, sin Tj, Tk. Helix, same thing. And here T naught is given by 0. Now let's see. St, we set up the arc length function by using the formula. So T naught from 0. And here, for the upper limit, we change this into T, same as the variable here. St equals 0, integral 0 to T, integral square root cosine tau derivative, so which is negative sine. So let's write down this direction. Okay, so going to be negative sine tau square cosine tau square plus 1 and d tau. So let's see, 0 to t, here going to be root 2 d tau, and after we solve this integral, it's going to be 2t. So you can take a look. St, actually the arc length now is a function in terms of t. For example, if I ask you to find arc length from from 0 to 5, so that means as 5 equals 10, right? So if we want to find the arc length from 0 to 100, what's the meaning of that one? That means we are looking for as 100, so which is 2 times 100 is 200. So by using the arc length function, you can find the arc length pretty quick. So for other, like when we have multiple questions. Okay, that is arc length function. Actually, why we want to learn the arc length function? Because we want to, we will use this for our future study. Now let's take a look at what is ds dt. Okay, so we know s is a function of t, right? So definitely for function, it has a derivative. ds dt equals what? Actually, ds dt, okay, I'm going to show you. So, okay, question. What is ds dt? Think about calculus 1. Do you still remember if we define a function to be fx equals, for example, 2 to x sine t dt. What's the derivative of this function? Do you still remember this? This is called the fundamental theorem of calculus. So when we take the derivative of capital F, that means kind of like a derivative of this thing, right? And the derivative of that one just equals sine x. Okay, just equals sine x. Now, this is a review of Calc 1. Now let's take a look at what is our ST. 0 to t. And here I'm going to write down the easy case. Okay, r prime tau theta. So this is like in calculus 1 is like tau is like a t, right? So what is s prime t? It's just like a r prime t. Change tau into t. Something, same thing. So actually ds dt equals the length of the derivative of the tangential vector. Okay, ds dt equals this one. So in the future, we may use this conclusion. So another application of the arc length function is parameterize a curve with respect to arc length s. So it's look like this. Okay, so parameterize a curve with respect to arc length s. So what's the meaning of this one? Before we have rt, for example, equals xt, yt, zt. And what's the parameter? T is the parameter, right? But right now we want to express this by using the s. Okay, arc length is like xs, ys, zs. We want to use this to s as the parameter. I'm going to show you how to do that. In our last example, st for this rt, which is cosine ti, sine tj, tk, and st equals what? Let's take a look. St for this is example 2, right? St equals root 2t. And now by using this equation, we can solve for t. So let's see, what is t? T equals s over root 2. And now we plug this into our vector function rt. So let's see, what is our rt? Our rt becomes what? Okay, cosine t, and t now is s over 2. And sine s over root 2, j. And plus tk, t is s over root 2. Okay, and you can take a look. What are the parameter right now? They are all s is parameter, right? So we can also write down this as rs. So this is called parameterize a curve with respect to the arc length. So that means we can write down the vector function in terms of the arc length.